We've got here another centripetal motion question, but this one's on a banked track. So there's a bicycle going around the track, and this is another angle just to show it. And the first question that a lot of students actually missed in this was this question 5 here. Some students saw a picture and then jumped straight to question 6. But question 5 is asked to draw two arrows on figure 2b, on this one here. Two arrows to show the forces acting on the bicycle and the rider. Now, a common mistake was to draw a force going this way and call it the centripetal force. I'll explain why that isn't an answer in a second, but the actual two forces are a downwards force for gravity and a force perpendicular to the surface, normal force. Now the rule is the reason centripetal force is not a force is because actual forces, you need to be touching for there to be a force. The only things that don't need to touch, no touch, that we deal with at the moment are gravity and magnetic force. Those are the only ones that don't need to touch an object to apply a force. So in this case, what's applying force? Gravity. It doesn't need to touch, but there's a downwards force from gravity. And the only other thing touching it is the surface of the road, so that gives it a normal force. Now if you add these two forces together, and the gravity down here, you get the overall force, that direction, which is the centripetal force. Okay, that's an overall force, but it's not an actual force itself. So that's why it's not an answer. The second question is saying the path of the bicycle has a radius of 100. Bicycle is travelling at 10 meters a second. What is the angle of the bank so that the bike travels around the corner with no sideways frictional force between the tyres and the track? Right, so in this case, the formula that I have on my cheat sheet is that tan theta equals centripetal over of gravity. And the reason I have that is because it's this triangle here, normal. There's our normal force. Here's our gravity force down here, and this one here is the centripetal. So if we've got, this is mg, gravity, this is centripetal, we can work out the angle, and the angle ends up being this angle theta ends up being this angle up here. Theta are the same angle. So if we can work out that angle using this triangle, which is what I've got here, because tan theta equals opposite over adjacent, and there's the opposite centripetal, and there's the adjacent mg. So that's why I've got my tan theta equals centripetal over gravity force. So just write all the numbers in. The centripetal force we know equals mv squared over r, and the gravity force is equal to mg. Now when we go to put all the numbers in to work this out, they don't give us the mass of the bike. Turns out that's okay because there's a mass on the top and the bottom of this large fraction, and they cancel out. So we're left with tan theta equals v squared over r divided by g, which means tan theta equals v squared over gr. And put the numbers in. Tan theta therefore equals, v was 10 squared, over g is equal to 10, and r is equal to 100. 10 squared is 100, divided by 1000 equals 0.1. So tan theta equals 0.1. We take the inverse of that, tan negative 1 of 0.1. The answer that gives is 5.7 degrees.